I've uploaded the previous recordings on YouTube, and I've given you the link. Hopefully, you can follow them. So, where were we? We're going very slow. I mean, like when compared to topics we covered. Let's see. So, let me share my screen. So I'm assuming that from Monday we can resume our physical classes, right? Because I think the buses are moving now. Today I was not sure, so today we kept it online. But Monday onward we will restart the physical class unless there is something else, unless there is some other landslide. Right. So we were doing ML estimation, and this is what we covered in the previous class. So it illustrated the general procedure. We have a vector of parameters, and in this particular case, which we considered, we were looking at the Gaussian case with an unknown mean, multivariate Gaussian with an unknown mean vector and a known covariance matrix. And this is the parameter vector theta, and this is the likelihood for a single point. And essentially, the technique for maximum likelihood involves differentiating the likelihood function with respect to the unknown parameter and equating it to 0, and finding out that value of the parameter which makes the derivative 0. And this is what we did, and then you do it for all the points, and then you will get an estimate. You will get the maximum likelihood estimate. Okay, so today we will continue that, the same thing, but for a more general case. So in the previous one, we did not, we were having one of the parameters was known, but now we will look at the more general case. Again, we will stick right now to Gaussian. So it is now, okay, I should write the date. What is the date today? 22. 22/9/22. Okay. ML estimation. We look at the univariate case right now. Unknown mean, unknown variance. This is from Duda again. Okay, so our parameter vector theta is now this is the univariate case. So there is a mean and there is a variance which are unknown, which we will call theta1 and theta2. This is our parameter vector, and we are now going to compute the likelihood for a single point P of these xk's are now scalars because it is a univariate Gaussian. This theta currently is unknown. And then I will just write down the likelihood minus half log of 2 pi theta 2, which is the variance, minus half theta 2 xk minus theta 1 the whole square. Right, so this is the likelihood function for a single point, where theta 1 is the variance. Theta 2 is the variance and theta 1 is the mean, and these are currently unknown. And now we need to apply the gradient. We apply this derivative operator over theta. This is my function L, likelihood function theta over L, which will give me, what will this give me? So you are going, because there are theta 1 and theta 2, we will first differentiate with theta 1, then we'll differentiate with theta 2. So when you differentiate this with respect to theta 1, this term becomes 0. So you will get 1 by 2 theta 2. Theta 2 is a constant. 2 xk minus theta 1. And this will give me nothing but xk minus theta 1 by theta 2. And this is the first part of the vector. This is with respect to theta1. The second part of the derivative will be, you have to differentiate this with respect to theta2. And that will give me, this is log of 1 by x. So this, this is log of x. Derivative of log x is 1 by x. And this is with respect to theta2. So xk into theta minus 1 whole square is a constant. So this will be theta2 to the power minus 1. The derivative of which will be minus 1 theta2 raised to minus 2. Okay, so this will give me nothing but minus 1 by 2 theta2 plus xk minus theta1 the whole square by 2 theta2 square. Okay, are you clear what we have done? We have just differentiated. We just applied chain rule with respect to theta2. Okay, we just differentiated with respect to theta2 here. So this is 1 by x, and this is a constant multiplied by minus theta2 to the power minus 2. That is what is coming in the denominator. So now we are going to equate this to 0. This is a 0 vector because there are two components. And that will give us, let's say we do it for all data points. We have, let's say, yeah, let's do it for theta1 first, which will be, so we have to find out, because these are two separate terms, we have to find out what is the theta1 which will equate this to 0. Right? And in that situation, theta2 is a constant. So let me just write that down. Summation k equal to 1 to n, where there are n data points in the data set D, 1 by theta2 xk minus theta1 equal to 0. This is nothing but this, right? 1 by theta2 xk minus theta1, this is equal to 0. We want to find out which theta1 makes this 0. Theta2 is a constant because it does not depend on theta1. So we can ignore the theta2 and that we will ignore, and then what do we get? K equals to 1 to n xk minus theta1 equal to 0, which will give me theta1 is equal to 1 by n sigma xk. K goes from 1 to n. This is nothing but the sample mean, which is also the maximum likelihood estimate. So basically it means that therefore what we conclude is the ML estimate for mu is x bar, which is the xn 1 by n k 1 by n, k goes from 1 to n, which is nothing but the sample mean. Okay, the sample mean. So the maximum likelihood estimate for the mu for the actual mean is the sample mean. What about the variance? Coming to variance, we will equate this term. You have to make this equal to 0. So that will give me. So I can actually remove the 2. Okay, 1 by let me write this down here. So this is minus 1 by 2 theta 2 plus xk minus theta 1 by 2 theta 2 square is equal to 0. Here, what theta 2 makes this 0? That's what we have to find out. Theta 1 is the constant. So this is just for one data point. So when you do it for all the data points, you will have. So I can straight away remove the half. The 2 will go. If I do it for all data points, I will have the summation k goes from 1 to n, 1 by theta 2 plus this summation over the whole thing. Xk minus theta 1 whole square by theta 2 square equal to 0, which will give me, again, I can just the summation 1 by theta 2 plus summation xk minus theta 1 square by theta square is equal to 0. Is there a negative term somewhere? Yeah, this minus. This minus. This is minus. So this gives me xk minus theta 1 whole square by theta 2 square is equal to 1 summation 1 by theta 2. Summation goes from k goes from 1 to n. K goes from 1 to n. And what will this become? This will, I can just remove 1 theta 2 because it is there on both sides. So xk minus theta 1 square by theta 2 is equal to n. Small n. This is going to be 1 if I remove the theta 2. So this will be 1. Sum to n times it will be n. So this will give me, this implies theta 2 is nothing but 1 by n sigma xk minus theta 1 whole square. K goes from 1 to n. Okay, so this is my theta 2. This is ML estimate of sigma square is equal to 1 by n. K goes from 1 to n. Xk minus theta 1 the whole square. And we know theta 1 previously that theta 1 is equal to x bar, which is the sample mean. Okay, and what is this actually? What is this term? This is nothing but this term is blue. This is the arithmetic average of square of deviation from mean. from the sample mean. Okay, so these are the two estimates which will be useful to us. I think ML estimate of variance and ML estimate of this is the ML estimate of variance, and this is the ML estimate of mean. Okay, so now another thing that you must remember is that this I touched upon last class. The ML estimate of mu is equal to x bar, which is the sample mean. But x bar is same as expected value of x, where x is the underlying random variable from which we are drawing the observations. Okay, so basically what this means is this estimate is correct. So that means the sample mean converges to the true mean which is E of x. The sample mean converges to the true mean if there are large number of data points. So as your n becomes very large, this small n, the total number of observations, as it becomes very large, the sample mean converges to the true mean. So this is a correct estimate. Now ML estimate of variance is not equal to E of x minus E of x the whole square. Okay, this is actually the variance. What I'm saying is the maximum likelihood estimate of variance is not equal to the true variance. Because if you look at the expression for so the maximum likelihood estimate of variance is not equal to the true variance, because this is a biased estimate. So there are two different things here. What is there is something called sample variance. What is sample variance? Sample variance is defined as 1 by n minus 1. K equals 1 to n xk minus x bar the whole square. This is sample variance. Again, this is usually represented as s squared. This is sample variance. And what are we getting here? The ML estimate. ML estimate for variance, there is, instead of 1 by n, it is a n. Okay, and the sample variance, expected value of sample variance is equal to the true variance. And true variance is what I wrote here, expected value of x minus E of x the whole square. But the ML estimate is not equal to the sample variance. The ML estimate is rather than dividing by 1 by n minus 1, rather than dividing by n minus 1, the ML estimate is dividing by n. So the ML estimate is always underestimating the true variance. Even if you have large number of data points, the maximum likelihood estimate of variance is not going to be equal to the true variance. Keep that in mind. So this is a biased estimate. Whereas this is unbiased estimate, the mean. ML estimate for the mean is unbiased. Okay, so just keep that in mind. So, so you have to factor in for this 1 by n minus 1. So usually you whatever the sample, the maximum likelihood estimate, you have to multiply by n minus 1 by n, so that you get the so that correction is applied to it, so that you get the a better estimate of variance. Okay, any questions so far? Did you understand what I was saying? Okay, so this is from Ruda Hart's book. Please read it when you get time. But just remember the difference. So we have done only for the univariate case now. But just remember that the ML estimate for mean is correct, and but the ML estimate for variance is biased. Okay, so that was for the univariate case. Now we can quickly touch upon ML estimate for multivariate case. That means there is a mu and there is a sigma. Both are unknown. So we follow the same procedure. Okay, so yeah, I'll just stop for a minute. If you can go through this, and if you have anything to ask, you can ask me. I'll just drink some water. Okay. Yeah, I hope we can do away with online classes, because this is not at all good. I have no idea what you guys are doing. All right, so we are recording, right? Yeah, we are recording. Okay, now we will look at the ML estimate for the multivariate case, when there is a mean vector and a covariance matrix. So our parameters vector is now mu and call it sigma, mean vector and covariance matrix, right? So this is the parameter vector. Let's write the likelihood function log of p for a single data point xk given theta. I hope I will use the variable names correctly. Let's see, this is xk. Okay. So x is a d-dimensional vector, right? Feature vector is of dimension d. So we have minus d by 2 log of 2 pi minus half log of determinant of sigma minus half xk minus mu sigma inverse xk minus mu. Okay, so this is my likelihood function, log likelihood function. And now we have to find out the derivative with respect to theta vector. So let's first do with respect to mean. So derivative with respect to mean vector is going to be I'm calling this function as L. So essentially, the mu of L, which is going to be, see, you can straight away see that there is no mu here. There is no mu here. So these two terms will vanish. I have only this quadratic form here. This is a transpose. This quadratic form here. And if I do it for all the values, sigma k goes from 1 to n minus half. Okay, so I have to apply the derivative of this. Okay, minus half xk minus mu transpose sigma inverse xk minus mu so the summation is also there. So now we have to use what we used last time. We have, if you remember, last time we had used the derivatives. Let's see. So let me just write that again here. Use matrix derivatives. So if you have some alpha which is equal to x transpose ax, it's a quadratic form. A is a symmetric matrix. X transpose ax, then d alpha by dx is equal to a plus a transpose x, and if a is symmetric, implies this becomes 2ax. Okay, so this is the one result which we'll use. The other result is another alpha is equal to x transpose ay, d alpha by dx is going to be ay. Okay, and we also have d alpha by dy is a transpose x. So this is similar. This is same as what we. So if you see the previous notes, I have written something here also. It here, matrix derivative. We use it here. I used it somewhere. No, it's not here. In different lecture. Okay. This is a lecture from previous time where we are deriving this Jacobian. So what I wrote here is this x transpose ax, and now here I had written x transpose ax. I had written x transpose a plus a transpose, whereas here I am writing a plus a transpose x. So this is basically the same. The only difference is that here x transpose a plus a transpose will give you in terms of rows, and if you take the transpose of that, you will get it in terms of columns. That is what we have done here. So this is the same thing in terms of columns. X transpose a plus a transpose. And similarly for alpha equal to x transpose ay, we had ay and a, we have ay and a transpose x, whereas here we had written y transpose a and x transpose a transpose, because this is again in terms of rows, whereas this is in terms of columns. So it doesn't matter which we are doing, whether it is rows or in terms of columns.
Hello.
You have a doubt? Okay. So we will use these results here today. I mean, it's easier to work in terms of columns, but it really doesn't matter because we are anyway going to equate it to 0. So whether you are doing it column wise or row wise, it doesn't matter. So now let us differentiate this. For that, first let us expand. Okay. So we are going to do derivative with respect to mu of, let me write it like this, k equals 1 to n. There is a minus half sitting outside. Inside this there is xk transpose sigma inverse xk minus xk transpose sigma inverse mu minus mu transpose sigma inverse xk plus this aside mu transpose sigma inverse mu. Okay, so we are going to differentiate this with respect to mu. So there is no mu here, so this term will vanish. So we have only we are only left with this. And this one, what I will do, just for the sake of convenience, I'm going to rewrite this one as mu transpose sigma inverse xk. These are all vectors. Okay, because A transpose B, X transpose A Y is same as Y transpose AX if A is symmetric. So because sigma inverse is symmetric, I have just renamed this as this, and so that will give me. I have not yet taken the derivative of k equals 1 to n minus half. So this one I'm going to just ignore now because this is going to be 0 when you take the derivative. Okay. I will just write this as 2 or minus 2 mu transpose sigma inverse xk plus mu transpose sigma inverse mu. Is it clear what I did? I just combined these two here. This is as such. This one I've ignored because derivative then is going to be 0. And if I apply the derivative, k goes from 1 to n. There's a minus half outside. So this that is this minus 2. We are going to differentiate with respect to mu. Okay, so I can use this form here. Mu transpose sigma inverse xk. I can write ay, which is nothing but sigma inverse xk. And the derivative of this is going to be 2. We'll use this result. 2 sigma inverse mu. And this is equal to 0. So I can get rid of the half. That minus half I'll just it inside. So I will get the summation k equal to 1 to n sigma inverse xk minus sigma inverse mu is equal to 0. Now what can I do? I can take the summation k equals 1 to n sigma inverse xk is equal to summation k equals 1 to n sigma inverse mu. Am I right? What are we doing? What are we doing? We want to find out, this is with respect to mu, right? Yeah. So in this case, our sigma inverse will get cancelled out. Anyway, it does not matter because now we are doing with respect to mu. So I get, these are our vectors. So cancel sigma inverse. So I will get k equal to 1 to n xk is equal to, the sigma inverse will be n mu. And this implies mu is 1 by n k equals 1 to n xk, which is nothing but your x bar, which is your sample mean. Okay, so the maximum likelihood estimate of mu, I should probably call it as mu ml, which is your mu ml. Its maximum likelihood estimate of mu is, again, you can see for the multivariate case, is equal to the sample mean. Okay. Yeah, we should do it for the covariance also, but since all of you are like zombies not saying anything, I will stop, and hopefully we can meet again on Monday. Okay, any questions in what we have covered so far? We have just used differentiation, that's all. Okay, I just have to manipulate with respect to vectors, that's all, but otherwise it's straightforward. And we have just derived the maximum likelihood estimate of mean for the multivariate case, and that is again equal to the sample mean. Yeah, anything you want to ask? Okay, you can. This is not there in Duda. I think it's a solved problem. Okay, I mean it's a exercise problem. I thought you should cover it. But yes. Okay. Also, the exam is now shifted to 6th. We will have it with the regular midsem exam schedule with the institute is having. Okay, so we will have it on 6th forenoon. That is the E slot.
So what will be the format? Like it will be optional or written?
What do you mean optional?
So multiple choice questions.
No. It will be pen and paper. Okay, and I have also created the assignment. I'm sorry, it was a little delayed. I have uploaded. I mean, I have not uploaded. I'll upload it now after this lecture. And I don't want to waste the lecture time explaining what to do in the assignment. It is a little involved. You have to spend some effort for it. But I will make a video which describes the assignment, what you have to do. You can watch that video. And the assignment is due on 22nd. Yeah, this is the assignment. I will upload it today. It's due on 10th October. Okay, it is due on 10th October. So you're going to do two questions are there. I will share it with you. I will also share some data. Individual assignment, and you need to submit a report on Moodle. And this is the format of the report, because we are going to automatically sort it, automatically process it. If your report does not have this format, then your submission will not be considered. So please make sure that it is correct. All small letters, okay. Then the report should include a Google Colab page with your code, because we want to run it and see. No point in sharing the code with me. It is better you share a Colab page. Okay, if the Colab page link is not there in the report, then you will not get marks. And the report you should write in the report you should write what you observe. There are many things you need to infer from the assignment, from the results you get, and you need to fill up some tables and make some figures. All of that you should put in the report. Okay, and you need to summarize the classifier performance. That you go through this in detail, and then I will show you. I will upload this on Moodle today. You can have a look, and I will upload the data also, and I will make a video explaining how to do the assignment. What is expected. Okay, that video might take a day, but just wait. At least one question you can start doing. So this builds mostly on base classification, discriminant functions, and decision surfaces. Right. Okay, so that is all from my side. Yeah, so we can meet on Monday, hopefully in person.
Sir?
Yes.
I wanted to